Graph traversal. Graph traversal is a fundamental concept in graph theory and computer science that involves visiting all the vertices or nodes in a graph in a systematic manner. Traversal is the process of exploring a graph to access each vertex and its associated edges, typically to solve problems such as searching, finding paths, or analyzing graph structure. Traversing a graph is a critical operation in various domains, including network analysis, social media, search engines, artificial intelligence, and more. The efficiency and nature of graph traversal algorithms depend on the structure of the graph, whether it is directed or undirected, weighted or unweighted, and sparse or dense. There are two primary types of graph traversal algorithms: breadth-first search, BFS, and depth-first search, DFS. Each of these methods explores the graph in distinct ways, with different applications and advantages depending on the problem at hand. Breadth-first search, BFS. Breadth-first search, BFS, is a graph traversal algorithm that explores the graph level by level, starting from a given source vertex. It systematically visits all vertices that are at the same distance from the source before moving on to the next level. BFS uses a queue data structure to keep track of the vertices to be explored. The process starts by placing the source vertex in the queue and marking it as visited. As long as there are vertices in the queue, BFS dequeues a vertex, visits it, and enqueues all its unvisited neighbors, ensuring that each vertex is explored once. This method guarantees that the shortest path to any vertex, in terms of the number of edges, will be found first. BFS is particularly useful in scenarios where the shortest path between two vertices is needed, such as in unweighted graphs or when determining the distance between nodes in a network. A common example is finding the shortest path in a maze, where BFS explores each possible route in layers, ensuring that the shortest route is found before longer ones. BFS is also instrumental in solving problems like connectivity in a graph, checking if two vertices are connected, finding connected components, and level order traversal in trees. One of the key characteristics of BFS is that it explores all neighbors of a node before moving deeper into the graph, making it well suited for problems like finding the shortest path in unweighted graphs or determining connected components. However, BFS has its limitations when dealing with weighted graphs where edge costs vary. It does not take into account edge weights, so it might not always return the optimal path in such graphs. Additionally, for large graphs, BFS can be computationally expensive in terms of both memory and time, particularly in dense graphs where many nodes need to be processed. Depth-first search, DFS. Depth-first search, DFS, by contrast, explores as far down a branch of the graph as possible before backtracking. This means that DFS goes deep into a graph from a starting vertex, exploring one path completely before moving on to the next unexplored branch. DFS can be implemented using either a recursive approach or an explicit stack data structure to keep track of the nodes to be explored. Starting from a source vertex, DFS visits a node, marks it as visited, and recursively visits each of its unvisited neighbors. This process continues until all vertices in the graph have been visited. DFS is a powerful traversal technique for tasks such as topological sorting, cycle detection, and solving mazes. In directed acyclic graphs, DAGs, DFS is commonly used to find topological order, a linear ordering of vertices where for every directed edge, U, V, vertex U comes before vertex V. DFS is also useful for detecting cycles in a graph, particularly in directed graphs. as it can help identify back edges that form cycles. By keeping track of the recursion stack or the explicit stack, one can determine whether a node is part of a cycle or not. Unlike BFS, which explores the graph level by level, DFS dives deep into a graph, exploring one potential path before backtracking. This property makes DFS ideal for problems like finding all paths between two nodes, solving puzzles like the 8 queens problem, or exploring all the nodes in a specific branch of the graph. DFS is also advantageous when dealing with sparse graphs and when the full exploration of a graph is needed. However, DFS can be inefficient in certain scenarios, particularly in large graphs where the algorithm may end up exploring long paths before discovering the solution, leading to a deep recursion or excessive stack usage. One of the main drawbacks of DFS is that it may not always find the shortest path to a vertex, especially in unweighted graphs. Since it explores one branch fully before moving on to others, it may traverse long paths that would have been avoided by BFS. Another challenge with DFS is that it may require significant memory for storing the recursion stack or explicit stack, especially in very deep graphs. Comparison of BFS and DFS. While both BFS and DFS are essential graph traversal techniques, the choice between them largely depends on the problem being solved. BFS is typically preferred when the shortest path is required or when searching in a graph that is close to being a tree. It guarantees that the first time a vertex is visited, it is reached by the shortest path. In terms of edges, on the other hand, DFS is often used when exploring all possible solutions, searching in deep or sparse graphs, or when dealing with tasks like cycle detection and topological sorting. Both BFS and DFS have their time complexity, which is generally O(V plus E), where V is the number of vertices and E is the number of edges in the graph. This is because in both algorithms, every vertex and every edge is processed once. However, their space complexity can differ. BFS typically uses more space, especially in dense graphs, due to the need to store all the vertices at each level in the queue. DFS, on the other hand, uses less space for sparse graphs but may require deep recursion stacks or explicit stacks in the case of very deep graphs. Applications of graph traversal algorithms. Both BFS and DFS form the backbone of many algorithms and applications. BFS is frequently used in routing algorithms for shortest path and network flow problems. It is also employed in web crawlers, where it explores the web by visiting links layer by layer. In social networks, BFS can identify friendship chains or the distance between users. DFS is often used in problems like solving puzzles, e.g., Sudoku or mazes, where the solution is found by exploring possible configurations and backtracking when necessary. It also plays a significant role in topological sorting, cycle detection, and strongly connected components in directed graphs. Furthermore, DFS is used in machine learning algorithms to traverse decision trees and find optimal solutions in search problems. In summary, graph traversal is a critical operation for exploring and analyzing graphs. The choice between BFS and DFS depends on the nature of the graph and the specific problem being addressed. BFS is ideal for finding the shortest path in unweighted graphs and analyzing connectivity, while DFS excels in problems requiring deep exploration, such as topological sorting and cycle detection. Both algorithms offer powerful tools for solving complex problems in a wide range of applications, from networking and AI to social media analysis and puzzle solving.